Now, our last speaker for this session, it's one of the invited speakers, Sina Zeytinoğlu from Harvard University. Hi, Sina.
Hi.
You can share your screen. Good morning, by the way. It's very early. Yeah. Thank you for joining us. Okay, and the title of his talk is Quantum Signal Processing and Optimal Hamiltonian Simulation with Rydberg Atoms, please.
Hi, everyone. So I would like to first thank the organizers for inviting me and giving me this opportunity to share with you our work on quantum signal processing. This is a work that I've done with Sho Sugira from MIT and also from the NTT Phi Labs. And this is the link for our work, which is on archive right now. So yeah, so it's morning here, and I may be a little bit scattered. So if I may miss, I hope not, but I may miss a point or so. So you can try to make sure that you're following by asking questions. Okay, let's see. Okay, so the motivation for our work is basically compiling quantum algorithms on quantum hardware. As of course we all know, quantum computation has the promise of giving some exponential speedups for certain computational tasks. These can be related to solving linear equations. It can be quantum simulation or factoring. This is all very interesting and very promising and great. However, there is somewhat a problem when it comes to actually implementing these algorithms in real quantum systems, and that is the reason for this kind of the disjunction between theory and experiment, if you wish, is that these algorithms often use some sort of query, some sort of assumptions on the data input, right? So like if I'm solving linear systems, I am somehow assuming that I have access to the matrix, whose entries that I know, for instance, right? So how am I going to make the quantum computer know these entries is just somewhat like assume that I can input such data into the quantum hardware, right? So these are the queries. So there's some black box function that allows me to input this data or calculate some function. So the advantage comes based on the assumption that I have this black box function that I can have my quantum computer compute already. So then we would like to compile these unitaries in a way, right, like these black box functions, to such that we can implement it on quantum hardware. So this is what we want to do. These compilers, if you wish, their performance will be measured by a few metrics, such as when I implement my algorithm, I want to make sure that I'm not doing it in a I'm doing it in a way that the errors are not happening as little as possible. So for instance, like the simplest example, I'm not going to store my quantum information in a state that has radiative decay rate, right? So I want to use such states to manipulate the system instead. Other metrics such as are including time to execute it, right? So or like the number of ancillary qubits that I need outside of my system, such that I can manipulate the system. And also for some implementation, scalability could be an issue. So I want to be able to, if wanted, increase the instance size of the problem that I'm approaching. Okay, so of course, yeah, in the beginning, it may be, one may think that this is too hard because we don't even have a common language. Right? So we have a bunch of functions. How are we going to think about those functions in a common language, and also in a way that we can actually implement in quantum hardware. Recent work has underlined the use of block encoding unitaries, which are unitaries which kind of has encode some operator in the block of a unitary, as its name says. And interestingly, these block encoded unitaries are rather simple to manipulate. and through these manipulations, you can generate very complex functions of the block encoded operator A here. So there are two different things that you can do. Both are quite general. One is arithmetic, right? So which means that if I have two block encoded unitaries, I know a simple way how to add them, right? Or I know a simple way how to multiply them, right? Multiplication is kind of what we are used to from unitaries, but we can also add them. And so I can form any polynomial, right? Through these kind of arithmetic trees. I can build some arithmetic tree that computes some function like this. But moreover, there is another tool that we will refer to as quantum signal processing, which interprets this operator as the signal operator, right? And then the point is to try to build functions, some polynomial functions from it, without, but from this A only. So on the arithmetic side, we could have multivariable polynomials, but now we're having a single variable. And yeah, so we can do this, it turns out, again, using simple instructions that can be implemented in experiment. And of course, yeah, both of these are quite powerful, right? So because we know that any function that we can think of that's smooth enough has quite some error scaling, with respect to its polynomial approximations. And then this error depends on the smoothness, and if the function is smooth enough, then the error scales rather favorably. And now, just to give you some examples about, okay, what are these functions, for instance, that I would like to construct using these techniques, is, the simplest one is, of course, Hamiltonian. If you want to think about Hamiltonian simulation, think about A as the Hamiltonian, and then you want to implement the exponent, the time evolution operator, right? That's generated by this Hamiltonian, and then there's a polynomial approximation to this function, right? So, or we can formulate, it turns out, the fixed point Grover search in the same way, or quantum phase estimation if we also include the measurements. So where the polynomial is a Heaviside theta function, right? So it really looks like, like these block encodings are very powerful. I can do any function, but in particular, we know ways to explicitly do Hamiltonian simulation, search, and estimation, which really points at the power of this block encoded technique, and it's the opportunities that we have to basically compile some query some compile some queries and oracles in the query model, right? So that's a good thing. But now then the question shifts then, right? So that kind of in the abstract level we answered that. So we want to implement the block. We want to understand what it takes to implement these block encodings in a real system, right? So to actually really realize these algorithms and the physical system. So for this, we are choosing a physical system, although the kind of the Hamiltonian that's needed is not so is not so special. We are choosing Rydberg atoms in optical tweezer arrays. So the Hamiltonian describing interactions of these in this platform is just two body interactions that are that are non-local, right? One reason why we chose this Rydberg atoms is with tweezer arrays is, of course, that these tweezer arrays are amazing. And in recent years, people have really shown the different ways that one can arrange the atoms in 2 and 3 dimensions. And, you know, in such a way that the interaction length scale is large compared to the separation between 2 atoms. I mean, so we can have these networks that we can work with. But choosing a system like this also gives us constraints from the control perspective, that we only have, you know, we have a bunch of atoms, we want to, how do we control them? We shine laser on them, right? So the kind of Hamiltonian terms that we have time-dependent control on are single qubit rotations. And this constraint turns out to be rather important. And now we are not talking about, you know, like, we don't want to restrict ourselves to some effective Hamiltonian when you're driving and, you know, trying to maybe engineer your Hamiltonian with like larger, higher order terms with time dependence. We are just sticking with, you know, the real interaction between the light, semi-classical light, and the atoms. Okay, so we further restrict ourselves to a certain, you know, like a certain class of a certain way of decomposing this so-called signal operator, or this operator that's block-encoded, which is, you know, this expansion, which is a sum of multi-qubit Pauli operators, which are acting on n-site systems qubits, right? So, and then we're saying that, you know, these Paulis are at most k local. Notice really quickly that these alphas need to be, you know, like they need to sum up to something smaller than 1 because they're going to be encoded in a unitary, right? So yeah, with these assumptions, we show the following scaling. So one thing that we show is that because of this kind of single qubit control, you know, that at each time that I have one frequency kind of, you know, or few frequencies acting on a single qubit, the time that it takes to block encode such an operator is can be parallelized, or, you know, can be reduced in a sense from your naive guess, which is n, you know, the number of Pauli operators, by only n site, right? So in a sense, because each qubit needs to go through some evolution, and then you can only condition that only on one. You know, you can only have one type of evolution, if you wish, on the system size. It is not so good looking, but still, you know, these things. So there's a mistake here, but like, so for if I'm thinking about some geometrically local Hamiltonian, for instance, this is as a sum here, then I would have, I'm sorry, like there's a constant. This time would take constant, so it's actually not so bad. On the other side, you know, if I have a k local Hamiltonian, then the number of ancilla that I need is still going to more or less scale with n site, right? With k more or less is constant, you know, compared to n site. So that's quite good. So for every system atom, I have one ancilla, kind of. And but more, the most interesting thing about this is that the error rate. The point is that what we can kind of compile, we can find gates that are native to Rydberg atoms that reduce the error rate for block encoding such an operator. So if I have a k local Hamiltonian, the number of errors, if you wish, counted in terms of C0 operations, is going to only scale with the locality of the largest locality of the terms. So which means that you know, the error cost of implementing a geometrically local Hamiltonian encoding it in this way is only going to be constant. So which is a quite amazing thing. So from scalability, yeah, our protocols are going to be all scalable. But I will focus mostly on this error rate. Yeah. So our main contributions. So what we do is that we show that block encoding unitaries can be compiled into shallow circuits that are using simple and efficient gates generated by the native Hamiltonian of the Rydberg system. And then we see that this block encoding of linear combination of unitaries, what I showed, the linear combination of polys, can be expressed associated with a tree structure, which then allows for a robust error-robust implementation of these block encoding unitaries. And well, error-robust when they're biased errors, and then we then design some Rydberg protocol that has biased errors. Biased errors, when you have a control gate, if the control condition is satisfied, error happens. If it doesn't, error doesn't happen. So that will be our goal. And then we have a case study of optimal Hamiltonian simulation based on quantum signal processing. So it's optimal in the sense that number of gates, for instance, grows with the space-time, simulated space-time volume. So yeah, tools that we use are, for these errors, we use electromagnetically induced transparency to realize some biased error model. And we use we make sure that we use the constraint of local qubit control, and we use one-hot encoding as a way of efficiently implement the operations that I will talk a little bit more about. Okay, so I hope everything is not too confusing until now, but so I just want to take a step back and tell you a little bit more about this block encoding unitaries. So they can be really thought about as a generalization that generalization that allows us to describe computation more generally. So if I have so let's say that I want to act on this state, through some black box function that gives me A times psi, right? But in general, maybe I don't want A to be unitary, right? I mean, I want to apply the Hamiltonian on the system, and then take expectation value or something. So because of this, what I need to do is to use some ancillary qubits, and maybe I use some ancillary qubits and then post-select on some measurements, right, to realize this. So in this case, let's say for concreteness, I have some ancillary qubits all in 0, and then what I want is to have a unitary which only if it stays all zeros, then an A is applied. And otherwise, I have some state which is orthogonal to this flag, if you wish, right? So this ancillary state is being all 0. So you see, so I can separate the two. I can distinguish these two possibilities where A is applied or something else is applied on psi. And this immediately gives me the form of, block encodings. So this is, just I think it's a way to clearly think about what block encodings are, and how general they are is kind of obvious from this kind of perspective. As I said, so now we are going to talk about one way of implementing these block encodings of linear combinations of unitaries. And then let's try to see the structure in linear combination of unitaries. So I have all these combination of a bunch of Pauli operators. How can I make a unitary that block encodes it? Is actually very simple. There's this 3-step protocol to block encode A in this form. And then, the V here is some kind of state preparation of the ancilla. So I make the ancilla go to a bunch of address states, I call them, in their Hilbert space. And then what we do is that for each one of these address states, right? So it's we have some kind of ROM, or you can call it RAM, which says that I take each one of these addresses, and if I emit that address, then I apply some unitary. And then what we do at the end is to undo the state preparation part and that gives us the desired block encoding, right? So this is how this works. Okay, so let's think about this from a more like, data-oriented way, because we are trying to compile an algorithm, which means that we have some classical description of the thing that we want to, implement, and we will need to somehow communicate that to the quantum system. So from this perspective, we can think about like this. We have this A. There's some alphas, right? Like these coefficients that we need to communicate. And then we need to communicate, which polys these things are. So, and then this I do through these, binary valued variables R and S. So S is for support, R determines whether the poly is X, Y, and Z. So how does this U, the composition of U for the linear combination of unitary load this data? So obviously, so we have a data tree. Sorry, I skipped that a little bit. So we have a data tree that we organize this data in. Organize this data in. So in the first part, in the first level of the tree, we only have the coefficients, right? So I choose one of the polys, and then for each poly, I again have like for each side some whether the support is 0 or 1. And like then I have the information on like which poly it is. Okay, so then this V, the state preparation part, creates some states that amplitude encode these amplitudes, and then acting on each of these address states, I load the information about the poly operators. Right? So this is in the second part. So this is the way that the block encoding through a linear combination of unitaries loads the data of the classical description of this matrix that we want to apply on the system. Okay, so okay, that's kind of okay, but like, what is the use of it? So there are a couple of things that this data tree tells us. Like one thing is what I told you about like local control. So if I have this local control, then each qubit can be connected to only one subtree of this data tree, right? So like I cannot have both multiple paths conditioning the evolution on the same qubit. So, and this directly gives us the maximum parallelization rate, and then the result that like how long it's going to take to implement this. So that's one kind of trivial thing that almost trivial thing that we can see from, or we can see trivially from this tree. The other thing is like kind of a promise, or like some hope that if I somehow can sample through these like subtrees as I'm doing them, that like my errors scale only with the coefficient, right? Then it's going to be very nice, because then the errors are going to be, the first level is going, is going to really reduce the errors, because the probability that I am in, if I have alpha 1, the probability that the address state is on that state is going to be growing with alpha 1. So if I can make gates such that the gate errors are only there when the conditional on that state, then the total error rate is going to be smaller. Okay, so how much time do I have? I need to, maybe I need to skip something.
You still have time. You can go, but we can stop 19, and you have 10 more minutes.
Okay, sounds great, Okay, so that's one question that, as I hinted at before, like we are going to try to do that. So we're going to implement some gates such that, like the error is biased. So only if the condition that tells me that I am going to this subtree is satisfied, then I get some error. But if this, the address state is not that, then I'm not going to introduce errors. And the second thing is, of course, these different address states, if I want to implement things conditioned on different address states, I need to have an efficient way of, distinguishing between the address states. If it takes me a long time to distinguish each address states, then it's going to take longer time, right? And then most likely I'm going to need a lot of operations to distinguish between them. and that's going to also introduce errors. So that's the other thing that we can, aim at by looking at such a data tree. And this is just a reminder. So we will try to find ways to, make address states that are easily distinguished, and also we want to make some conditional unitaries which are biased in the errors. Okay, so now we came to some more, physics part, if you wish, like depending on your orientation. So first, I will talk about how to make these biased errors using Rydberg blockade. So let me just give you a small animation for Rydberg blockade. So what happens is that if you have these two Rydberg atoms and you shine light on them and they're separated far enough, then you have a way of detecting if the atoms are excited or not. Then it's kind of easily accessible. You can measure this, and then see that these atoms can be excited like independently of each other. It doesn't matter if the other one's excited. So in particular, they can be both excited at the same time. So, but let's say then we can bring these atoms together such that they somehow feel these clouds that are drew around. And what happens then? I shine lasers for both of them, but when I look at what is excited, I always see either one of the atoms are excited or the other one. Right? So then this is the kind of the blockade. One of excitation in one of the atoms blocks the excitation of the of its partner in this case. Okay, so let's use this to implement some logical gates. How can we do this? So there's this very important protocol to do this by Yaks et al. So let's say that there are two atoms that are feeling each other, right? So then if I apply this pulse sequence where the numbers are the sequence of pulses on these two atoms, then it turns out that this is the same as some controlled NOT gate, right? So how do we see this? So if I have some, let's say that the upper register is the control register and it satisfies the condition that I'm looking for, right? So I want to apply a NOT gate on the target. So let's say it's in 0, but okay, I drove only the one in the control register to the Rydberg state. So in this case, there's no evolution on the control register. So there's also no errors. But on the target side, I'm going to apply these 3 pulses that make sure that there's a NOT gate, right? So as I'm doing that, I'm assuming that all these logical states are much longer lived than these Rydberg states. So we'll see how they relate to what I talked about before. And in this configuration, depending on the state of the target register, I'm going to excite this qubit to the Rydberg state, and then there's going to be some radiative decay. Right. So let's see what happens when the condition is not satisfied. So I'm sending in 1 from the control register. Then with the first pulse, I excite the control to the Rydberg state. And then this is going, because of interactions, or because of what causes this blockade effect is that there are interactions between Rydberg states. And when I excite the control qubit to the Rydberg state, then the target Rydberg state is going to be energy shifted, making these transitions more or less not possible. So then what happens? Then I don't apply any operation on the target qubit. So then together with what I talked about before, this realizes the C0 gate, right? So in terms of errors though, what happens here is that, okay, so because I am in 1 here, I excite Rydberg state, so there's radiative decay there. Okay, so I have decay. And also for the target, there's no decay perhaps. I mean, there could be, but through some intermediate state, but there's some non-adiabatic error because this blockade is never perfect, right? So the energy shift is never so large, and we want to think about large systems. So this can become an important error source. So the main point here, though, is that the error occurs like in both cases. Either the control condition is satisfied or not satisfied. In both cases, it occurs. So this is not what we want. We want to change something such that the errors are biased. I want it to be such that, you know, only when the condition is satisfied that I have errors. So how do we do this? We use EIT, electromagnetically induced transparency, on the target register. Okay, so what happens here is then, you know, like if I have the control is not satisfied, so I switch the controls now, so but it's not so important. So if I'm in the zero state, what's going to happen is that I'm not going to excite to Rydberg state as before, and then I have some EIT scheme on the target register, which does basically nothing during the, if I have this control pulse, control field. I send the probe pulse, and then what it does is that it takes this logical manifold, you know, it stays in logical manifold, and then brings them, you know, evolves them through some dark, what we call the dark state, which doesn't have much contribution from, you know, any one of these other states, which are presumably short-lived, right? So in that case, nothing happens, and when in the other case, though, you know, of course, because I'm going to excite it to the Rydberg state, there's going to be radiative decay, and also, you know, then it's going to shift the Rydberg state of the target, and, you know, there's going to be some radiative decay. But important thing is that because of EIT, when the control condition is not satisfied, really nothing happens, and then the errors are very much reduced. So we can use this. We can use this method to implement the second part, this U bar, for the conditional unitaries. Right? So when I'm doing this tree, I'm going to go through the tree, and then the errors that I'm going to get is going to be proportional to the amplitudes that are depicted in that data tree. Okay, so the other thing that I say is that we need to be able to have these address states easily distinguishable. Like, what does it mean easily? It's like you have some local optical fields, and then somehow I can rotate the state to a very distinguished state, you know, if that's the state that I want. So somehow I want to flag these states very easily using only local gates without using too much time. And there's this kind of amazingly simple way to amazingly simple encoding that we can use, which is somewhat expensive, but it's like, you know, really does this very interestingly, I think, which is one-hot encoding, which says that, you know, if I have some n qubits, I am going to, you know, make sure that the there's only one excitation for each one of these address qubits. So what I can do is that I can look at, I can, you know, ask the question for, you know, optically addressing one qubit, and then if I get the flag, then I know exactly, you know, through one pulse, I know that the state is in this one hot encoded state rather than all the other n of them, right? So, but then the question is like, how can I prepare such a state? And then again, like Rydberg atoms are especially somehow tailored for this because of their long range interactions. Of course, I mean, if you have any like two-body interactions that's long range, it still works. But what we can do is that we can put a bunch of Rydberg atoms next to each other, and you know, if they all feel each other, then when I send laser light that's exciting all of them, I'm going to get at most one excitation, right? So whenever I have any excitation in any of the qubits, then I'm going to, you know, block all the others. So what this does is that it really reduces the Hilbert space, which is relevant to describe the evolution of this many Rydberg system. And, you know, like what we do is that if you start from all zeros, we shine this laser with some profile, right? And it turns out we can basically directly encode the amplitude of the or the Rabi frequency at each side to the relative amplitudes of these one-hot encoded states, right? So if I have these alphas, all I need to do is to shine the right, you know, size of the shape of the light, that gives me this state. So the nice thing about the other nice thing about this is that, you know, it's constant time. I don't need to do any more manipulation. I can just shine light, and as long as everyone feels each other, I'm going to get this nice superposition of one-hot encodings that are very easily distinguishable. And then once they're so distinguishable, I can apply this error, biased error controlled unitaries to implement the block encoding. Okay, so basically that's what we did, and then we wanted to benchmark this approach, and then we just estimated all the errors and then the depth that's needed, and we wanted to think about optimal Hamiltonian simulation because it's optimal, right? So like, and then we want to, and what's important is, once you're optimal is the overhead that you have, and what we want to do is to reduce the overhead as much as possible using the techniques that I talked about before. Yeah, so then we compared some different quantum simulation protocols or techniques that are based on just quantum signal processing, some quantum signal processing with some decimation, and the kind of the most popular Hamiltonian simulation algorithm based on like fourth order product formulas, which have been like shown that there are many ways to compile these fourth order algorithms using numerical optimization, right, on the circuit that gives you good performance. So we wanted to compare to the best performing the result in the literature, and then to be able to compare it, we did the same. We used the same Hamiltonian as was used in these works, which is this disordered Heisenberg model. And so these techniques that I described before allows us basically really reduce the errors, or like this error bound gate count, which is just counting how much error I have in units of a single CNOT. So we can really reduce it more than an order of magnitude compared to like this numerically optimized circuit for fourth order product formula on the Rydberg atom platform. For this, like the simplest, it's quite simple one-dimensional disordered Heisenberg model. So I mean, and we expect that the quantum signal processing is going to work better when we have higher order Pauli terms, etc. So this is very nice. So we, there's some promise there. On the other hand, there's a.
Sorry,
yes,
Sina.
this is my last slide.
Okay, thank you.
Yeah. So on the other hand, the depth. When you think about the depth, it looks like the overhead in terms of depth is much larger for the QSP based algorithms. So then you need to kind of make a decision. So these are errors that are coming from your gates, but you may also have some the coherence mechanisms that just happen when the qubits are idle, and then then maybe you don't want to use QSP for in this case. Okay, yeah. So that's our final result. So this conclusion outlook. So what I want you to take home is that block encodings are a natural solution to compilation problem. It allows us to describe these functions that we want to implement on quantum computers, and that kind of tells us how to realize them in quantum systems. And Rydberg atoms allow for efficient implementations of these block encodings that are robust to errors. So for future work, we can think about, we can measure these expectation values of block encoded operators, and we can make functions of them, so we can measure arbitrary response functions. So how are we going to use them to some advantage? And also, thinking about what are the how expensive is a given function, in a more systematic way for block encoding. Okay, thank you for your attention. That's all.
Okay, thank you. And now we can have questions. Let's start from a question from YouTube. and you can see it also on the chat box. And I'm going to read it for the audience. It's a question from Bülent Yılmaz, and he asked, how does block encoding method compares to Hamiltonian power methods, quantum power method, for time evolution of quantum systems with the same order of error?
So, yeah, so you can take, using the quantum signal processing, you can also do, take powers of the Hamiltonian. And then basically, I mean, I guess the answer is that, as I said, there's this optimal Hamiltonian simulation algorithm for geometrically local Hamiltonians, which is based on quantum signal processing. So that's optimal, right? So like in terms of comparison, if you have a local Hamiltonian, the quantum signal processing really is the optimal that you can get in terms of gate and time complexity. So usually, as I try to emphasize in the very beginning, these polynomial approximation methods, rather than looking at each power of in a Taylor series, I guess that's what you mean, the Taylor series. Yeah, basically, the error scaling of the polynomial approximation is very good. It's logarithmic in 1/epsilon. So I hope that gives some perspective.
Okay, thank you. Any other questions? I think we can have one more question, if there are any. Let me check. I think there is something on the chat box again. Yeah, it's from Onur Mucalılar. Sorry. Okay. Yeah, what is the current experimental situation? Has any algorithm been already implemented using Rydberg atoms?
Yes, that's a very good question. Basically, that's what we want to do. But like given the situation in Rydberg atoms right now, where they just kind of showed, like these spin liquid ground states of Hamiltonians, etc. Like for them, and also these quantum scars to work on that, it is not so easy to push them towards doing this kind of digital, if you wish, Hamiltonian simulation when it comes to Hamiltonian simulation. So that's kind of one of the reasons that we would like to use maybe the power of QSP to improve some measurement protocol that can happen using very small number of ancillae and signal process what you measure from the system. So yeah, and the comparison between this kind of time evolution through Hamiltonian versus circuits or versus the QSP is not always so easy, although there's some interesting recent work by Jens Eisert, for instance, trying to compare the complexity, compare the time evolution through Hamiltonian versus this kind of more discretized circuit evolution. So I would like to discover that more, and then maybe find a more convincing argument for digital Hamiltonian simulation, before we get super great qubits, for these NISQ era experiments. But yeah, that's really something that I would like to see happening. But right now, there are no efforts because of what I said. Yeah, thanks for the questions, by the way.
Okay, thank you. And Onur also thanks. I have some questions, but we are already over time, and maybe I can write to you directly.
Or Gather Town, we can.
Yeah, we can talk in the Gather Town. Okay, let me thank once again all the speakers, and Sina, thank you for very early morning. You gave us this nice talk, and thanks Carol and Onur. And with that, I'd like to say goodbye. This is the end of the second session.